Good morning, everybody. Today is the 18th of September, and we've just turned in our first quiz covering chapters 1 and 2, and we were developing a schedule to get us through the next section, chapters 3 and 4. The reason that I've developed this schedule is because on the 13th of October, that's officially the day of our midterm exam, which will cover chapters 1 through 4. And I wanted to leave a day free to review for the midterm exam. So that means that working backward, on the 9th of October, we will finish chapter 4. That's a tentative date. We may be a day or two off. But basically, that gives us 5 periods, 1, 2, 3, 4, 5, to cover chapter 4. So we'll begin chapter 4 on the 29th of September, which means that we have 5 class periods beginning today to cover chapter 3. Now, the topic of chapter 3 is torsion or twisting, and there are 10 sections in chapter 3. However, sections 3.6 through 3.10 are optional, and so we will cover sections 3.1 through 3.5 in class. And the rest of it will actually, depending on if you take an advanced mechanics of materials or strengths of materials class, you may cover the material in that particular, in sections 3.6 through 3.10. But in this class, it is not required and not appropriate to cover that material. All right, so today we're going to cover section 3.1, and we're going to start to lay out the geometry of torsion, and we're going to put in some definitions, why we study torsion, and sort of the geometry that we can study when we're talking about this. All right, so in general, torsion refers to two different things: an applied torque and a twist, a corresponding twist that goes along with it. It's very similar to a moment in the sense that torque has dimensions of a force acting through a distance, and that twist is defined by an angle, which dimensionless can be expressed in radians. And then, of course, we can convert radians, pardon me, to degrees. Now, one of the things that we do when we work with torsion is we often restrict our conversations to shafts of circular cross-section. And there are two reasons for that. One is an engineering reason. Most power shafts, are circular, and the other reason is a mathematical reason, the high degree of symmetry. Okay. Now, if we take first of all, I guess one of the things is what are we studying? Well, one of the main considerations of a torque is that by applying a torque to a shaft, this is an engineering consideration, we can transmit power. And this happens all the time. Anytime that you have a power takeoff, anytime that you have a drive shaft, anytime that you have a motor that spins, you're always putting power from one place to another. In other words, transmitting power. And that's one of the basic engineering considerations of a shaft, for example, a generator, or a turbine, or anything that rotates. What we basically have, I'm not even going to try and draw this, I'm going to put it up on the board for you. But this is in your textbook on page 149. And you can see that if you have a generator, a rotation, a turbine, basically what goes on is that you spin the shaft and you move power from one side, from one place to another. Now, this is a little more complicated. We will discuss power, but today we're just going to talk about what happens to a drive shaft or a power transmission shaft when we put a torque through it. So we're sort of starting the conversation on the geometry. So having said that, one of the things that we do, as I said, we always talk about or we often restrict our conversation to a shaft of a circular cross-section. And we basically state that if we apply a torque to it, that we have an equal and opposite torque that will twist the shaft through some amount of a degree. Now, one of the things about, if you look at the face of a shaft that's being twisted, we'll subtend some sort of an angle when we do this. A circular shaft, because of the high degree of symmetry, if it's twisted, we're not talking about a free spin, we're actually talking about a resistance to a spin and something actually twisting. The cross-section will remain in a plane or planar and unwarped. If you have a different type of a cross-section, like if you have some sort of a key that you subject to a torque, what will happen is the face of that key will become warped, and sometimes it's planar, or in other words, sometimes it remains in a plane, but sometimes it also dimples. And if it does that, the math just becomes progressively more complicated. So if we restrict our conversation to circular cross-sections, the math is easier for us to handle. This type of an application becomes important at points of our study. However, like I said, at this point we can learn a lot using a power transmission shaft. I actually have a blown up key that I want to show you, so I'm going to take a minute and run back to my office and go get it. So you're still on camera, because if I shut it off, it'll actually write over my other podcast. So anything you say, I guess will be held against you. So you'll be broadcasting to the world. 29 people are listening.
What did that say about planar and unwarped? It says something planar unwarped. Remain. Oh. Will remain.
Yeah, I can't read that. I couldn't either.
Yes. It wasn't indicated there.
No, it's that's what we go with. I think.
That's what I remember when I go.
I'm going to pass this around. Like I said, it was I knew exactly where this was, but I'm going to pass it around. I'm going to put it up on the screen for just a moment. This was a shaft, a gear, and a shaft with some splines, and there are 3 bolts, and there's also a key. This is called a driftwood key, and basically what happened here is this element failed at the wrong spot. So what it did then was, the official term is, it blew up. So this previously circular shaft is no longer a shaft and is no longer circular, and is just kind of really interesting to look at. But this is what happens when you subject things to torque and they do not behave the way that you would expect them to. You also see the bottom of the key right here when I pass it around, and you can see that it failed here, and it failed here, and it also failed here and here. Where it's really supposed to fail, something like this is supposed to fail on that key, and then it just goes into free spin, and then nothing gets damaged except the key, and then you can realign everything and put a new key in it, and everything is as good as it can be. So a key in this particular case sort of acts like a, it's not electrical, but the way that a fuse acts, you know, or a breaker, in the sense that you don't want your house to burn down. So if you start to put too much power through an electrical circuit, you want the breaker to pop or the fuse to blow. And so it's like a safety valve. And that's the way the key is supposed to work. And obviously here, this is the mechanical equivalent of having your house burn down. So you can take a look at that and pass it around. But it's a wonderful, I love that. I love that so much. It's just, it's a very cool thing. It's one of my prized possessions for showing how, what, this is like the don't let this happen to you kind of scenario in terms of power transmission. So anyway, while you're looking at that, let's take a look at the, I'd like to start with a cleaner piece of paper. So I'll put this underneath it. All right, so what we're going to do to simplify our discussion is to consider if we have a circular cross-section shaft. In other words, a shaft in the shape of a cylinder affixed to a wall. Now, once again, while the main reason for having a circular shaft is power transmission, we're obviously not going to be transmitting anything if we attach it to the wall, but it will allow us to entertain what happens to the geometry of the shaft if we subject it to some foot-pounds or Newton meters of torque. Right. So the first thing we do is we define the geometry, and on the cross-section, when we have this torque applied to it, we consider that at the center of the circle, the center of the cross-section, that no movement occurs. But as we go up to the distance of the radius, which along the radius we're going to call the distance rho, as rho increases from 0 to r, or the radius of our particular circle, we can look at a finite element and recognize that it's being subjected to some force, which we would call, since it's an element, dF. And so the torque on the entire cross-section then is actually the summation of all of these rho dFs. You might have a rho here and a rho here, but everywhere there's a finite element of force, and that the torque over the entire cross-section could be thought of as being rho times dF. Well, we also know, if you think about this, what kind of a force or what kind of a stress is this? If we talk about normal stress or shearing stress. If we're torquing something and we're looking at the cross-section, they're on the same plane, aren't they? So are we talking about a normal stress or shearing stress? Normal would pull, shearing would be on the same plane. So we know that tau is, we have a tau instead of a normal force. There's no normal force induced by a torque in this configuration. And we know that tau is equal to some sort of a force over some sort of an area. Or we could say that force is equal to tau times area. Or we could further say that dF, if tau were constant, which we're making that assumption, would be equal to tau dA. So I can rewrite my integral as rho tau dA. Okay? And we have a mathematical, not terribly useful yet, but we have an expression for a relationship between a torque and a tau. So we can say then that T, which is torque, which has dimensions of force times distance, or force times length, and tau, which is shearing stress, which has dimensions of force per area, or force per length squared, are related by distance from center and area of the cross section. We've not really said anything about what that relationship is, but from looking back to the integral then, we can say torque causes tau, or tau is a result of a torque. So let's explore that a little bit more. Oh, I also wanted to show you, they do a better job of drawing the deformations in circular shafts and non-circular shafts. But basically what they're saying is that as you subject a circular shaft to a torque, that the deformation does not change the geometry of the cross-section, whereas you can see when you twist a non-circular shaft, you have this sort of warping and dimpling of that cross-section. And as you can imagine, now that you've seen what the integral looks like, that dA is going to be really nasty, isn't it, when we start to integrate over the whole thing. So the dA remains very nice to us for a circular shaft and not so nice for a non-circular shaft. Okay. So once again, we have circular shaft stuck in the wall, subjected to a torque, and it twists. If we look at that initial cross section, if we look at a radius that used to go from 0 to A, point A, when we subject it to the torque, point A moves up some distance. This is greatly exaggerated under most circumstances to some point A prime, and we subtend an arc, AA prime, by the angle, which we call the angle of twist, which is designated by the Greek letter phi. Okay? So phi is the angle of twist on a cross section due to a torque. Okay. All right. Well, if we consider on the, and this is always hard for me to draw, so your authors do it better, but I think it's important that I give it the old college try here. So here is my circular shaft, and this end is stuck into the wall, so it's not turning anywhere. If I started with the length of that circular shaft, and I started with that original radius, which we could call C is equal to the radius, and rho is the distance from the center along the radius. I'll get my hand out of the way in just a minute. Okay, so from here to here is C, from here to here is L. As I subject it to a torque, and I move, if this is still considered, if we still call that point A, and I twist through some angle phi to point A prime, I also twist, since this is stationary, up to that same A prime point, and this length we could just call, it's still going to be L because we're remaining unwarped, but this angle is what we call gamma. And as you remember, gamma is the shearing strain. We learned that when we were talking about blocks deforming. Do you remember when we subjected a stress block to a shearing stress? We said that it warped to this sort of a configuration where these angles were previously all 90. Now this is 90 minus gamma, this is 90 plus gamma. This is the same gamma. This is shearing strain. It's how much of an angular deformation we have taken up on the length or on the axis of this structural member, this shaft. And if you notice, the arc A to A prime is the same on this triangle, on the triangle on the axis, and the triangle on the cross section. So that means that phi and gamma are related, and basically we can say that gamma times L is equal to phi times rho. Or that, since what we're really interested in is shearing strain, be equal to this. And if we go clear out to the edge, we can say gamma max is equal to phi times C over L, because C is the maximum value for rho. And that finally, we can relate maximum gamma to gamma at any point by the term rho over C. All right? And what this does basically is just has us relate shearing strain to maximum shearing strain to the geometry of our shaft, and eliminates this idea of angle of twist. All right. Now, from our previous discussions of gamma, we also know that gamma if I plot tau versus gamma, and I remain in the elastic range, that the slope of that line is G. And that's a direct analogy to the first drawing that we had, where in the elastic range, the slope of this line is E, right? So we're always talking about stress, strain, slope, stress, strain, slope. So from this, we know that G is equal to tau over gamma, or that tau is equal to G times gamma. And we can relate that back and substitute in these equations. And we can say then that G times gamma, which is tau, is equal to rho over C times, I guess it would be G times gamma max. Or that gamma at any point, let's do this, I don't even like that. We can bring those two equations together, and we can say, they skip a few steps in your book, but it comes out to be that tau is equal to rho over C times tau max. And what this is telling us is that on that cross-sectional face, the tau at a spot increases when we subject it to a torque. The torque has to be the same, but the tau here is going to be 0, and tau here is going to be a maximum, and that there's a linear distribution on that cross section. So tau at 0 equals 0, tau at C equals tau max, and the in-between, if we use this as being C, this is 0 to C, and this is rho, and this is, I should put this over here, this is my gamma axis. Gamma is 0 here, and it goes to gamma max. And that relationship is linear, a linear function of how far you are out along that radius. All right. So, since we have 4 minutes left, in the interest of time, you can bring these equations together in a useful form. What we have right now is only useful in understanding the geometry so that we know what we're talking about. But basically, tau is equal to torque times rho, the distance from the center, over J, which J is the polar moment of inertia, which are tabulated for circles and other common shapes in the back of your book. But basically, it's equal to the integral of rho dA. And you may or may not remember that from statics, but also that tau max then is equal to Tc over J. So the big important thing is J for a circle, which is all we're really interested in here, is equal to 1/2 pi times c to the 4th power. The only other type of a circle that we would have would be a hollowed out circle, which would look like this. And these hollow shafts are, from an engineering point of view, these are also shafts that we use to transmit power. So if we start at the center, if these have to be concentric circles, and if we call the radius of the inner circle, or that annular space, C1, and the radius to the outside circle, C2, that's going to equal 1/2 pi times C2 to the 4th minus C1 to the 4th, right? And so as long as we restrict our discussion to circles and hollowed out circles, then, and we get to do that, which is the nice news, that we don't have to worry about the other polar moments of inertia. But if you look here, for example, on the back cover of your book, J sub O, 1/2 pi r to the 4th, that's exactly what we've written for that J sub O. If we had a rectangle, on the other hand, J sub C is 1/12 base height times the quantity base squared height squared, which is quite a bit more complicated. We also have polar moments for ovals, quarter circles, half circles. This one is kind of ridiculous. So anytime you get into a shape like a triangle, you really have to go back to the original integral form to find J. So we're just going to use circles and hollowed out circles. So just so you know, there will be no surprises. There will be no rectangle with a star cut out of it in the middle of the next exam or anything like that. So if you get into a situation where you need those things, you will learn them as you go. All right, so at that point, we have actually finished section 3.1. So for your homework tonight, let's do a couple of easy problems. Not easy, I don't mean easy, but some kind of down-to-earth problems to get started. For our homework, let's do chapter problem 3.1 and 3.3. And we need one more, but we haven't started talking about anything about power transmission. Let's just do I'm debating between 3.5 and 3.9. Let's do 3.9, and I'll just show you. This will just get you used to doing a cutaway again. We've done these before, but basically what we're doing is we have pulleys, and we have torques exerted on the pulleys that would be transmitted to the shafts. And you just have to decide by doing a cutaway. For example, you can say that the torque here is just going to oppose that, so it's 6.8. But when you get down here, it's going to be 6.8. These are in opposite directions, minus 10.4. And if you do the math on those, you'll see that they come out to be this, because you could also cut it away this way. Okay? All right. 3 problems for homework, and have a wonderful day. And I will turn off our streaming, and then I will put these up on our middle page. So there we go.